will be covering we will continue with our series. So in this session, we will take the PYQs for 2017. We will cover 2017 set 2, 2016 paper and 2015 paper. And the questions that we will be addressing will be for the subject of heat transfer. So let's get started. So yes, as I told, we'll cover heat and mass transfer. So the question number 1 that we have for 2017 set 2, the question is arrange the metals aluminum, copper, iron, silver in increasing order of thermal conductivity. So let's look at the values, that what is the value for the thermal conductivity. Thermal conductivity is important when we are studying conduction through solids, or basically thermal conductivity is important when we study conduction through solid, liquid and gases. Right now the material which are given to us, they are all solids. Okay, so let's look at the value for the K for the different material that we have. So let's start with iron. So for iron, the value is 80 watt per meter Kelvin. So this is the unit of thermal conductivity for iron. For aluminium, the value is around 237 watt per meter Kelvin. For copper, value is around 401, and for silver it is 429. Okay, so higher K means higher thermal conductivity, it's a better conductor of heat. Lower value of K, that means is comparatively poor conductor of heat. Okay, so if you look at now, we have to arrange in increasing order. Okay, so K should increase. So lowest is iron, then is aluminium, then is copper, and then silver is the highest one. So the answer will be A here. Okay, so pure simple problem. If you remember the values of the metals for thermal conductivity, you can simply rank them in the increasing order. Okay, let's move to the next problem. Okay, now the question here is what is, let's read the question. Which of the following is false? That means which is not correct. Heat flow by conduction is directly proportional to the area and temperature gradient. Let's look at Fourier's law of heat conduction. Fourier's law of heat conduction, what it says, the heat flux normal to the direction of heat transfer is minus K. Okay, let me not write heat flux. I will write here the total heat transfer rate. The total heat transfer rate normal to the direction of heat transfer, or normal to the direction in which we are calculating the heat transfer, is K times area times dt dx or dt dn. So let's say if this is our block that we have for reference. Let's say this phase is have maintained at a temperature T1. This phase is maintained at a temperature T2. This is the direction normal n in which we want to calculate how much heat is getting transferred via conduction along the direction n. Then Fourier's law of heat conduction says that the heat transfer rate by conduction is minus Ka dot T dot n, where K is the thermal conductivity of the material, A is area normal to the direction of heat transfer, and dot T dot n is the temperature gradient in that direction. Okay, so here the question is heat conduction, the heat flow by conduction is directly proportional to area. Yes, it is proportional to area. It is proportional to temperature gradient. So this statement is true. Heat flow by convection is directly proportional to area and temperature difference. We know Newton's law of cooling, what it says, Q is heat transfer by a convection is H, heat transfer coefficient, times the surface area times the temperature difference between the solid surface and the free stream temperature, that is the fluid temperature. Okay. So if you look at the heat transfer by, this is heat transfer by conduction, and this is heat transfer by convection. So heat transfer via convection is proportional to surface area. Yes, it is proportional to surface area. It is proportional to temperature difference. Yes, it is proportional to temperature difference. So this statement is also true. Let's look at the third statement. Heat flow by radiation is directly proportional to the cube of absolute temperature of the radiating body. Okay. What is Stephen-Boltzmann law? Stephen-Boltzmann law says that the radiation emitted by a black body which is at a temperature T. Okay, so how much radiation is emitted, or the emissive power of a black body which is at a temperature T is given by sigma times surface temperature raised to power 4. Okay, and if we are calculating the emissive power of a real surface, then it is nothing but emissivity times sigma times Ts power 4. So it is not proportional to the cube of the absolute temperature. It is proportional to the fourth power. So this statement is the false here. Okay. Emissivity of a perfect black body is unity. Yes, it is unity. So this statement is true. Answer here is answer number C. C is the answer for this. Let's move to the next problem. Let's look at this problem. The temperature, the distribution of temperature T at a particular instant. Note the student, this is very, very important. At a particular, so he is telling you at a particular instant, he is mentioning the temperature distribution. So temperature distribution of temperature T at a particular instant across a large concrete wall 1 meter thick, which is heated from one side, is given by the equation. So he has given you the temperature distribution equation. T is 150 minus 80x plus 16x square, where x is the distance is in meter, T is the temperature in degree C. Thermal conductivity of the wall, he has given you 0.6 watt per meter Kelvin. Cross sectional area, he has given you 10 here, 10 meter square. Okay. Now, what we need to calculate is heat accumulated in unit time at this instant. What is the heat which is getting accumulated? So let me tell you the answer, and then we will see how we get this answer. So answer is 192 joule per second. Answer D. Let's see how do we get this answer. Okay, let's go ahead and look into the answer. Okay, so look at it. This is the plain wall that what we have, and he has mentioned the temperature distribution. So the temperature distribution, if you look at it, the temperature distribution is 150. Let's go back. Let's look at it once. It is 150 minus 80x plus 16x square. So it is 180 minus 80x plus 16x square. So if you look at it, at t x equal to 0, if you substitute x equal to 0, you get 150, just numbers. And if you put x equal to 1, you will get a value of 86. So this end is at a higher temperature, this end is at a lower temperature, and then you have a this kind of a relation, second power relation, a polynomial relation in the temperature distribution. So temperature is continuously decreasing like this. Okay, now let us see what he's asking us to find. So if we take this entire wall as our control volume or as our system, let us say, whichever way you feel convenient, let us say this is our system, and we can then apply the energy balance, law of conservation of energy. At so we write now law of conservation of energy for a particular instant. So what it says, total energy coming inside the system, or the rate at which total energy is coming inside the system, minus rate at which total energy is going out of the system, plus rate at which energy is generated within the system is equal to the rate of change of energy stored within the system. Okay, let's look at it now. Is there any heat generation happening inside our system? No. So there is no heat generation happening inside system. Is there heat coming inside the system? Is there heat going out of the system? So look at, he has not specified any convection coefficient, any lower temperatures, fluid temperatures on both the sides. So how do we calculate E in, E out? Very simple. He has given you the temperature distribution. Let's find out dt dx. So we find out dt dx. dt dx is minus 80 plus 32 times x. Let's calculate dt dx at x equal to 0. That is how much? It is minus 80. Okay, minus 80. So let's calculate Q conduction, which is happening at x equal to 0. Let's calculate this. This is minus K A dt dx at x equal to 0. How much is this value? K is given to you as, how much it is given? It is given as 0.6. Okay. Area is 10. dt dx is minus 80. How much is this value? Let's look at it. So this will be 6 480 watt per meter square, or not watt per meter square, it should be watt actually. So 480 watts. So what is 480 watts now? 480 watts is the energy coming inside the system through this phase. And this energy is coming via conduction. Okay. So we calculated this. Now let's do the same calculation at this phase. How much energy is going out via conduction? So this is our dt dx. So dt dx. Now let us calculate at x equal to 1. Once we calculate dt dx at x equal to 1, what value you get? 80 plus 32. Value of dt dx is how much? Minus 48. Now let us calculate q conduction at x equal to 1. What do you get? Minus k. K is 0.6. Area is 10. dt dx is minus 48. So value comes out to be how much? 288 watts. So this is the energy which is going out. So this is the energy which is, or the rate of energy coming inside the control volume. And same way, this is the energy which is going outside the control or outside the system, you can say. Look at the students, energy coming inside the system is not equal to energy going outside the system. That is why your stored energy of this system is going to change. And that is what it is asking you. Okay. So if you substitute now E in minus E out, what do you get? You get DES dt is 480 minus 288. Value comes out to be 192 kilojoule or joule per second, I think so. Joule per second. Let us verify again the previous one. Let's go to the previous slide. Yes, joule per second. Yes, it's not kilojoule, it's joule per second. Okay. Hope this answer is clear and the method is clear. Let's go to the next problem. So with this, we have covered 2017 set 2. Now let's start the 2016 questions. Look at this. A beaker is filled with hot water. Okay, so we have a beaker, and in that beaker, we have hot water. So this is our hot water inside the beaker. Hot water. Okay. And then what we are doing is that hot water, we are keeping it inside a room which is cool. Okay. So what happens? This hot water then cools down. The beaker filled with hot water in a room cools from 70 to 65 in T1 minutes, 65 to 60 in T2 minutes, and from 60 to 55 in T3 minutes. Okay. Then he is asking which of the statement is correct actually from here, which is the right answer. Whether the time taken, so T1 is greater than T2 is greater than T3, or all times are same, or which is the T3 will be the largest, T2 will be the second largest, and T1 will be the minimum, or cannot be concluded. Answer is option number C. Let us see how do we get this answer. So if you apply a lumped capacitance analysis, right, to this hot water, which is getting cooled now, okay, so you get an exponential cooling curve. So let us say this is T minus T infinity. Let us say the ambient temperature of the room is, let us say, T infinity. So this is losing heat. This is a hot water. Initially, it is at a certain temperature Ti, initial temperature, which is very high as compared to T infinity. With the passage of time, it is cooling. So what kind of cooling curve or what kind of temperature distribution that we are going to see, not distribution within the water, but distribution, when I say temporal distribution with time, how the temperature of the water is going to change. So it is going to change, it is going to follow an exponential variation. Considering, let's assume lumped capacitance method is valid, so it will be T minus T star. Your T star is your thermal time constant. Thermal time constant is rho Vc by Ha. So you have to understand this is an exponential cooling curve. So once you understand this is an exponential cooling curve, you will understand how the option is option C. Let's look at this. Okay, next slide. So this is our exponential cooling curve. Okay, so this is the cooling curve. So initially the water is at temperature Ti, and then it is cooling down with the passage of time, and it is asymptotically approaching the room temperature. Okay, so now let us say when the initial, look at this exponential curve behavior. Okay, so let us say you want to reach, let us say this temperature difference. What we are talking is from 70 we are going to 65 degrees. Okay, so 70 to 65 degrees, this is the time T1. Okay, and then second one is from going from probably, let us say, 60 to 65, 65 to 60. This is the time. So what you see, because of this exponential nature of the cooling curve, okay, initially your cooling rate will be very high. Initially the cooling rate is very, very high, and slowly the cooling rate, as the time progresses, the cooling rate is decreasing. That's why you will reach faster from 70 to 65, you will reach in lesser time. And as you proceed further in time, for the same temperature difference cooling, you will get a you will get a larger time. So that's why your T1 initial cooling time will be lesser as compared to the cooling time later, and the later time will be the largest. Okay, now let's move to the next problem. If the temperature of the sun is doubled, the rate of energy received on the earth will be increased by a factor of what? So, sun is a black body. Okay, sun is a black body. Okay, so for a black body, if I want to find out what is the energy emitted by the sun, it is nothing but I can use Stephen Boltzmann law, that is sigma Ts to the power 4, where Ts is the surface temperature, outer surface temperature of the sun. Okay, now what he's saying, we are increasing the temperature 2 times. So let us say how much the energy will be increased. So EB1 by EB2, that is emissive power of a black body, which is like at the sun temperature, let us say sun only. Okay, so this will become TS2. Let us say this is our temperature TS2, and this is sigma TS1 powerful. Okay, now TS2 is 2 times TS1. So EB2 by EB1 will become 2 power 4, which is nothing but 60 times. So your energy emitted by the sun or the energy received by the earth will be increased by a factor of 16. So answer is D. Okay. Let's move to the next problem. Transmission of heat by molecular collision. What it is called. So this phenomena is basically, this mode of heat transfer is referred to as conduction. So in convection, we know heat is basically getting transferred because of the bulk fluid motion. So my surface, I have a hot surface and there is a bulk fluid motion. Because of this, let us say my fluid is at a lower temperature. Because of this bulk fluid motion, heat get transferred from a hot surface to a cold fluid by a mechanism of convection. In case of radiation, I may have two surfaces which are at different temperature, TS1, let us say this is TS1, TS2, this is TS1, and TS1 is greater than TS2 is greater than TS1, then there will be a net radiative heat transfer from TS1 to TS2. Okay. And this mechanism doesn't require any medium. It can happen in vacuum also. And we can assume that this radiative heat transfer is happening in the form of electromagnetic wave propagation. Conduction, what happens in conduction? So in conduction, in a medium, if I have one surface at a higher temperature as compared to the other surface, then heat get transferred through the solid by a mechanism which we call as conduction. And in conduction, what happens? Energy gets transferred by molecular collisions. There is no net motion of the, there is no net bulk motion of the molecules. So molecules are just vibrating about their mean position, and hotter molecules are colliding with the colder one, the one which are a colder one, and that's how the energy just get transferred from one hot end to the other cold end by a mechanism of conduction, which is nothing but the heat is getting transferred by molecular collisions. So answer is C here. Let's move to the next problem. So here we have, let's look at this problem. So we have two ends of a rod of length L, radius R, made of same material, are kept at same temperature difference. So important thing to note, they are of same material. Okay. So let us here this problem is related to conduction. Same material means conductivity is same, and they are kept at same temperature difference. So delta T is also same. Which of the following rods conduct most heat per unit time? Okay. So basically, if you imagine, so this is your rod. Okay. So let us say one end of the rod is maintained at a higher temperature T1, other end is maintained at a lower temperature T2. This is the length of the rod, and this is the cross-sectional area of the rod. Now heat is getting transferred via conduction along the length from this end to this end. Okay. If you use Fourier's law, so you get heat transferred via conduction is K times area times T1 minus T2 by L, or you can say it as T1 minus T2 divided by L by Ka, where L by Ka is your resistance. Okay. So your RTS, thermal resistance, in this case is L by Ka. So lower the value of thermal resistance, higher will be the heat transfer rate for the same temperature difference. For the same temperature difference. Okay. So answer, what we need to find it out, which of these following configuration it is having the least thermal resistance. So if we get the option where we are having the least thermal resistance, that option corresponds to the maximum heat transfer rate. So let's calculate that. Let's move to the next slide and calculate those values. So let's take the configuration 1. So RTH, as I am saying, L by Ka. Okay. So K is constant for all the materials, what all the configuration that is being given. So L is 50. Let us put it at 50. 50 is like 50 into 10 to power minus, I will put it 2 because that is in meters. Then I have K. K is a constant factor. Area, cross-sectional area is given pi r square into 1 into 10 to power minus 4. Okay. So for first option, what resistance I get? I get 5,000 by pi times K. Okay. This is the number which I get for the thermal resistance. Let us do for the second. Second case, we have length as 2 centimeters. A is a constant factor. Area is 0.5 square into 10 to power minus 4. If I simplify these things, I get a value of 800 by K times pi. Let's calculate for third configuration. Here L is 100, that is 10 to power minus 2 times K. Area pi r square 4 into 10 to power minus 4. Once we solve this, we get 2500 K times pi. Okay. And fourth configuration, when we take 3 into 10 to power minus 2 K times pi times radius 1 into 10 to power minus 4, here we get 300 K times pi. Okay. So if you compare now these values, okay, the last option has the lowest thermal resistance. So it has the maximum heat transfer. So answer for this particular problem is D. Okay. Let's move to the next one. Thermometer works on what principle? So thermometer basically works on the zeroth law of thermodynamics, which says that if a body A is in equilibrium with body B and body A is in equilibrium with body C, then B and C are also in thermal equilibrium. Okay. And zeroth law of thermodynamics basically gives the concept of temperature. Okay. So our thermodynamics, it works on the zeroth law of thermodynamics. First law is concerned with law of conservation of energy. Second law of thermodynamics are your what? Kelvin Planck statements for a cycle, thermodynamic cycle, Kelvin Planck statements and Clausius statements. Okay. And second law of thermodynamics gives the concept of entropy. Okay. Zeroth law gives the concept of temperature. Okay. And thermometer works on the zeroth law of thermodynamics. Okay. Let's go to the next problem. Here what we have a flat plate. The length of the flat plate is 1 meter. Width is 50 centimeter. Is placed in an airstream at 30 degrees, blowing parallel to it. Convective heat transfer coefficient is 30 watt per meter square Kelvin. Heat transfer if the plate is maintained at a temperature of 400 degrees. So this is a simple case. You have hot surface and there is a cold fluid flowing over it. Heat transfer happens via the mechanism of convection. Use Newton's law of cooling. So say Newton's law of cooling, Q is H A T S minus T infinity. So S is the surface area from where the heat is getting transferred. So in this case, if you look at the plate, length is 1 meter. Okay. And width is how much? 50 centimeter. Okay, so if you calculate Q, he has given you H is 30. Okay, area is 1 into zero point 0.5. Okay, so this is the surface area which is available for convection heat transfer times the surface temperature of the hot plate, which is 30, and the free stream temperature is 30 degrees. Let's see what answer we get here. So let's do the calculation. H is 30, surface area is 1 into 50 centimeter, zero point 0.5 into surface temperature is 400 minus the free stream temperature. So we get this value as 550 watts, 5550 watts, which is nothing but our 5.55 kilowatt. So this is the answer here. Okay, let's move to the next problem. It is required to insulate the kitchen oven by a cork board. He has given you the thermal conductivity so that the heat loss from the oven does not exceed 400 watt per meter square. If the inner surface of oven is 225 degrees, the outer surface of the oven is at 40 degrees, the thickness of insulation required is. So this is a simple application of the Fourier's law of heat conduction. Let's draw the diagram. So this is, let's say this is the surface of the, this is the oven, probably the, what we are talking about, the insulation that is placed on the oven surface. So what is mentioned here is that this surface of the oven is maintained at 225 degrees. Okay, the inner surface, let us say the external surface, is maintained at 40 degrees. And this is the insulation that we have. Thermal conductivity of the insulation is 0.043 watt per meter Kelvin. So now what happens, you have this side is the oven. So from heat will get transferred from the oven to the external side, from towards the ambient side. Okay. Now what you are trying to do, probably you are trying to put an insulation over the oven surface so as to reduce the rate of heat transfer. Okay. So here what is being mentioned here is it is required to insulate the kitchen oven with a corkboard. So this is your corkboard, which is mentioned here. Thermal conductivity is 0.043 watt per meter Kelvin, so that the heat loss from the oven does not exceed 400 watts. So he has already given you Q conduction here, which is how much? 400 watt per meter square. Okay. While the inner surface is maintained at 225 degree, outer surface is at 40 degrees. Let's apply Newton's, not Newton, the Fourier's law of heat conduction. Q dot is Ka T1 minus T2 by L. Okay. And L is something which we need to find, which is the thickness of this insulation. Let's say this is L for us. Okay. So Q dot by the area, this becomes your heat flux. Okay, and this is given by T1 minus T2 by L. Okay, so how much is this? This is 400. T1 is 225, T2 is 40, and L is something which we need to find out. So L comes out to be how much? 225 minus 40 divided by 400. Wait 1 minute. Sorry, here this should be divided by K, one factor. I have missed the factor. Okay. So let's look at it again here. Let me erase this part. Let's calculate here what is L. So L will be K times this is 185 divided by 400. Okay. So how much is K? K is 0.043. Okay. Four three times 185 divided by 400. Let's calculate this. So we get a value of L as 1.988 centimeter, which is nothing but equal to 2 centimeter. Answer is B here. Okay. Simple application of Fourier's law of heat conduction, heat transfer through a plane slab. Okay. Let's move to the next problem. Okay. A radiator in a domestic heating system operates at a surface temperature of 55 degrees. Assuming radiator behaves as a black body, the rate at which it emits radiant heat per unit area is very simple application. See, he has mentioned you that it is behaving as a black body. What he is asking you, what he is asking, how much radiation it is emitting. Use the Stephen Boltzmann's law. The emissive power of the black body is nothing but epsilon is sigma Ts power 4. Important thing is temperature should be in Kelvin. So EB will be what? Sigma is 5.67 into 10 to power 8. Temperature is 55 degree. So substitute here 328 to the power 4. So let's calculate how much we get as an answer. So we get an answer as 656 watt, which is nothing but watt per meter square, which is nothing but 0.66 kilowatt per meter square. Answer is answer A. Let's move to the next problem. A gray body. What is a gray body? A gray body is defined such that monochromatic emissive power of the body is independent of temperature. Monochromatic emissive power of a black body is dependent on temperature. Monochromatic emissive power of a black body is independent of wavelength. Monochromatic emissive power of a body is dependent on wavelength. Answer is C. So gray body, in case of when we say a body is a gray body, then means the properties, the surface properties of that bodies. For example, epsilon, the emissivity, or the absorptivity, or the reflectivity. These properties are not function of wavelength. They are not function of wavelength. They are independent of wavelength. Okay. So gray body approximation or gray surface approximation assumes, in that approximation we assume that these surface properties or the properties are independent of the wavelength. They do not vary wavelength with the wavelength. Okay, so that's the gray body approximation. So your monochromatic emissive power. So what it wants to say is the emissivity. Let us say epsilon lambda here. That is what is the emissivity of a body at a particular wavelength with respect to lambda. If you see it, this will be a single value. This is not going to vary with respect to wavelength. For a non-gray body, epsilon lambda can vary with, this is a step function approximation, or it can vary with wavelength in a different form also. So it would be a function. But for a gray body, it is independent of the wavelength. Emissivity is independent of the wavelength. So answer is C. Let's move to the next option. Next problem. Critical thickness of insulation. What is critical thickness? So basically, let's say you have a conductor, a current carrying conductor, a small conducting wire. Okay. Now, because there is a heat which is getting generated when you are flowing current through this conductor, right? Heats get generated. Okay. Our idea of always thinking is that whenever we add insulation on something, some conductor, it basically what it does, we always think from heat transfer perspective that it basically decreases the heat transfer rate. Insulation basically adds resistance to heat transfer, but that's not always the case. Okay. So critical radius of insulation. So if you look at it, if you plot the heat transfer rate with respect to radius, let us say if this is the radius, let us say this is the radius, and let us say this is the conductor we have, and on top of this conductor, now I am placing insulation, which is having a low thermal conductivity. And outside you have an ambient condition. Okay, your H is H naught, and let us say fluid temperature is T infinity. So heat is getting transferred. Now what you are doing, you are putting insulation. Okay, and always we think whenever we put insulation, it will reduce the heat transfer rate, but that's not the case actually. Okay, so let us say this is your RCR, and let us say this is the radius of the bare material. Right now we are saying this is R. So what happens? This is the curve it follows. So if your conductor, let us say I will take two cross sections. One is this cross section, and another is this cross section. So let us say this is my small wire that I see, the wires that I have, electrical wires. So radius of those wires are very, very small. Okay, as compared to the pipes, let us say from pipes from where the fluid is flowing, hot fluid. So this is the basically the pipe. Let us say this is the pipe what we are talking about. So this diameter is comparatively very, very small as compared to current carrying conductors. Okay, so what it says is that, so if your radius is such that it is less than the critical radius, okay, it is less than certain critical radius, and if you add insulation in that case, what happens? Your heat transfer rate actually increases. So you are adding insulation thinking, you think like it decreases, but in this case it increases. But after critical radius of insulation, let us say if you add any more insulation, your heat transfer rate actually starts to decrease. So let us say you have a wire such that this wire has a radius R, and let us say you add certain thickness of insulation, okay, such that this radius is R1. So if R1 is less than RCR, so you are in this regime, then your heat transfer rate actually increases. Okay. Let us say you have a steam pipe. Okay. You have a steam pipe, basically a pipe through which steam is flowing, and that radius is capital R. And capital R is very, very greater than RCR. Then if you are adding insulation, so this will be probably R. Then if you are adding insulation, then your heat transfer rate is decreasing. But in small copper conductors, if you add insulation, it increases the heat transfer. So critical thickness of insulation, which is nothing but critical thickness of insulation is RCR minus R. Okay. Critical thickness of insulation yields maximum heat transfer rate from a pipe. It doesn't yields minimum heat transfer rate. It is yields maximum heat transfer rate. Okay? It yields maximum heat transfer rate. Answer is answer number. Option is option C. Let's move to the next problem. Now, next set of question paper, that is for 2015. Let's look at this problem here. So in this case, what we have is basically we have a heat transfer problem where we have a plain slab. So we have two slabs. 1 and 2, and on one side of the slab we have a hot fluid, other side we have a cold fluid. Okay, so it's a steady state heat conduction across a thickness in a plain composite wall. Okay, he has given us on one side the heat transfer coefficient, the on the other side heat transfer coefficient, the temperature on the hot side, cold side, thermal conductivity of the first material, second material, thicknesses are also given. And what he wants us to calculate is the what is the interface temperature, and he is telling the contact resistance between the two surfaces is minimum, or we can neglect that. He wants us to calculate what is the interface temperature, that is the interface of 1 and 2, this temperature here, that is the interface temperature when we say this interface temperature. Okay, so how do we do calculation for this? Simple, draw the resistance network. Okay, start the draw the resistance network and you will get the answer here. So answer is 3.75. Let us see how do we get this answer. Okay, let's see how do we get this answer. So start with the resistance network. Let's move to the next slide and probably we can look at it. Start with the resistance network. So this is the node 1, which is our T infinity I, which is the hotter fluid. Okay, the first resistance is the convection resistance. So that is heat transferred via convection, then conduction, then conduction, and then via convection. Okay, so the first resistance, so let us say this is our T1, this interface temperature, this is T2, and this is T3. Okay, so then we have T1, so resistance will be 1 over HIAI. Then the second resistance, T2, resistance is L1 by K1A1. Then the third resistance, T3, L2 by K2A2. And then the third convection resistance, which is nothing but 1 over H naught A naught. Now areas are same. Areas are altogether same. He's asking us to find out what is T2. Okay. So whatever heat is getting convected, okay, same heat is getting conducted, conducted, and finally getting convected. Okay. So I can write the energy balance from here to here. So how do I write the energy balance? Look at it, this equation. So T infinity I minus T2 divided by the resistance. So resistance is what? 1 over HI. Areas are same everywhere. Plus L1 by K1A equal to T2 minus, let us say this is outer, T infinity naught upon L2 by K2A plus 1 over H into A. So areas are cancelled, they are going to get cancelled. T infinity I, how much it is? This value is 20 degrees. T2 is something which we need to calculate. HI is how much? It is 20. Li is 0.3. Ai is 20. T2 is something which we want to calculate. T infinity 2 is minus 2. So this will become plus 2 upon L2 is 0.15. Thermal conductivity is 50 plus 1 over H naught. H naught is how much? It is 50. Okay. So if you solve this, you get 0.023. You take this entire term, this term to this side, and this entire term to the other side. You get 0.023 into 20 minus T2 equal to 0.065 into T2 plus 2. Okay. You can solve this. It is 0.46 minus 0.023 T2 equal to 0.065 T2 plus 0.13. And solve this, you get T2 as 3.75 degrees. Okay. So what I have done here, so I have taken this part here. Okay. So I have taken this as the, so energy coming from via convection till this portion and conduction till this portion. That is what I have equated to get the temperature T2. Okay. Okay, that is because whatever energy is coming in, same energy is going out. And you can calculate Q is what, nothing but Q is delta T by R. Okay. So in one case, I have done what? I have done T infinity I minus T2 by R, which is but nothing but R convection plus R conduction of 1. And then I have done T2 minus T infinity naught as R conduction, which is in the second solid, plus R convection. So I have equated these two to find out T2. Okay. Let's move to the next problem. A coolant. A coolant fluid at 30 degrees flows over a heated flat plate maintained at a constant temperature of 100 degrees. So our flat plate is at 100 degrees. Coolant is coming at 30 degrees. The boundary layer temperature distribution is given to us. Okay, so let us say this is the temperature distribution, how it is varying. And this is our, let us say, y coordinate, normal to the plate. So this is the temperature distribution which is given to us. Okay. He's saying thermal conductivity of the fluid is 1 watt per meter. Then the local convective heat transfer coefficient in watt per meter square Kelvin at that location is, okay. So principle here is the layer, when the fluid flows over the flat plate, first layer comes in contact with the plate. Okay. And heat transfer to that first plate, which becomes stationary, is via conduction. And same heat is getting conducted via basically convection. Okay. So, so what happens to the first layer? The heat is getting transferred via conduction. And the same heat is then getting transferred to the bulk fluid via convection. Okay. So first layer, this layer which becomes stationary, right? To this, heat is getting transferred via conduction. And finally, to the bulk fluid, the heat is getting transferred via convection. So we are just doing an energy balance. So Q conduction is equals to Q convection. So Q conduction, in this case, this conduction is conduction to the first layer of the fluid, which is Kf into dou T by dou Y at y equal to 0. So I'm using Fourier's law. And this is equals to Q convection, which is H times Ts minus T infinity. Area gets cancelled on both the sides. So that's why I'm not writing area. You can write area and cancel it. So what do you get? You get H is minus K dou T dou Y at y equal to 0 Ts minus T infinity. Okay. So if you calculate dou T dou Y, what do you get? You get minus 70 exponential minus y. And where we want to calculate this dou T dou Y at y equal to 0. Exponential of 0 is 1, so this becomes minus 70. Okay, let's move to the next slide and solve there. Okay, so we got dou T dou Y as minus 70. Kf is given as 1. Ts is, I think, given as 100. And T infinity is 30. Let's apply. H is minus Kf. So minus 1 dou T dou Y at y equal to 0 minus 70. Ts minus T infinity is 70, 100 minus 30. So H is 70 by 70, which is 1 watt per meter square Kelvin. Let's look at the answer. So answer is B, 1 watt per meter square Kelvin. Let's move to the next problem. A furnace wall is constructed as shown in the figure. The interface temperature is will be how much? That is what it is asking. Very simple problem here again. So look at it. This end of the wall is at 100 degrees. So we'll draw the resistance network. Okay. So this is first a resistance. So heat will get transferred from temperature conducted from a high temperature surface of the high temperature to a lower. Okay, so heat will get conducted through the solid because one phase is maintained at higher temperature, other phase is at lower temperature. This phase is at 120 degrees C. So this is 1000. This is our T1. Then the other is 120. Resistance is L by Ka. Okay, L by Ka. So L for first is 0.3. K is again 3 divided by area. Let's keep the area here. Okay. In the second case, it is L is again 0.3, K is 0.3, sorry, and area is A. Okay. So whatever heat gets conducted through this solid, same heat will be getting conducted through this solid. So again, Q conduction from slab 1 is equal to Q conduction from slab 2. Okay. Let's try to apply that. Okay. Let's try to apply that. So if you calculate the resistance of first one, what you will get? You will get 0.3 by 3A, which is nothing but 0.1 times A. Okay. And second resistance will be what? 1 over A. Okay. Let's look at now. How do we solve in the next slide? So Q conduction in the slab 1 is equals to Q conduction in the slab 2. Okay. So T1, which is nothing but it's the T1, not say T1. I should not say T1. 1000 degrees minus T1, the first resistance, which is 0.3 by 3. L by Ka is equal to T1 minus 120, 0.3 by 0.3 into area. Okay, area will get cancelled. So you get 1000 minus T1, this is 0.1. This is T1 minus 120 equal to 1. Okay, this becomes 1000 times T1, 0.1, T1 minus 12 is 1012, 1.1 T1, and T1 comes out to be 920 degrees C. Let's see the answer. So the answer is 920 degrees C. Option C. Okay. Simple application of the conduction resistance network and the energy balance. Let's move to the next problem. See, we studied about the critical thickness of insulation, and there is a problem. For a current wire of 20 mm diameter. So diameter is how much? So 20 mm. So let now look at it. Its radius is 10 mm. This is the 10 mm radius. Okay. For a current wire 20 mm diameter exposed to the air, maximum dissipation occurs when thickness of insulation is. So you are adding insulation, okay, and you want maximum heat dissipation. So this is your Q, this is your R, this is your heat transfer rate. You want maximum heat dissipation. That means in that case, your radius, this radius should be RCR. That is, you have to find out what is the critical radius of insulation. Critical radius of insulation in case of a cylinder, because it's a current carrying wire is a cylinder, it's K by H naught, where K is the thermal conductivity of the insulation, which is 0.5. H naught is how much? 20. So RCR will become how much? So this is 0.5 divided by 20 into you do 1000 to that, what you get? 25 mm. 25 mm is your critical radius of insulation. But he's asking you what? When the thickness of insulation, he's not asking you critical radius of insulation, he wants to calculate, or is asking about the thickness of insulation. So critical thickness, if you want to say, that will be RCR minus R, which is 25 minus 10, which is 15 mm. Okay. So for a current carrying wire of diameter 20 diameter exposed to the wire, maximum heat dissipation occurs when thickness of insulation is 15 mm. And that option is not given here. So answer is D. Okay. None of the above. Okay. Let's move to the next problem. It is proposed, again, critical radius of insulation concept. It is proposed to coat 1 mm diameter wire. So radius is how much? R of the wire is 0.5 mm with an enamel paint. Conductivity is given. Okay, with an enamel paint. So this is your wire. On top of the wire, you are putting a coat of a paint. You are coating and putting a paint, and this paint is an enamel paint for which the thermal conductivity is given 0.1 watt per meter Kelvin. Very low thermal conductivity, like an insulator, but it increases the heat transfer rate. Why? Because diameter of the wire is very, very small. It will be lesser than critical radius of insulation. Okay, critical radius. Okay, with heat transfer coefficient H is how much? It is 100 watt per meter square Kelvin. So calculate the optimum thickness of the enamel plate. So let us calculate first the critical radius. Okay. RCR is K by H naught. Okay. So where K is the thermal conductivity of the insulation. Here your insulation is enamel paint, 0.1. And H naught, convective heat transfer coefficient, how much is 100? So if you do this calculation, you will get this as 1 mm. Okay. Now your R for the bare wire is how much? 0.5 mm. So if you have to increase the heat transfer rate, how much paint thickness you should add? That should be RCR minus R, which is 1 minus 0.5, which is 0.5 mm. At this thickness, you will get maximum heat transfer rate. Maximum heat transfer. So answer is B, which is 0.5. Let's move to the next problem if we have here. Okay. Three metal walls have the same cross-sectional area having thermal conductivity in the ratio of 1 is to 2 is to 4. So look at it. K1, let us say if this is 1, K2 is 2, and K3 is 4. Heat transfer, the transfer of heat at a rate of 1000 kilojoule per hour. For same wall thickness, the temperature drop will be in the ratio of what? Okay, so you have three metal walls of the same area having the thermal conductivity in the ratio of this. Okay, so we can imagine like this. Just imagine you have this kind of a distribution. So same heat is getting flow is getting conducted. So one case you have K1, second case you have K2, third case you have K3. Thickness L1 is same, L2 is same. Okay, so L1 equal to L2 equal to L3. This is same. Cross-sectional area A1 equal to A2 equal to A3 is same. If you calculate Q, let us say what is Q? It is Ka delta T by L. So if I say K times delta T, which is nothing but LQ by A. So my L is constant, Q is constant, A is constant. So K delta T is constant. So then I can write this as K delta T is constant, which is nothing but K1 delta 1, K2 delta 2 equal to K3 delta 3, which is nothing but it will be K1 is 1. So delta 1 times 2 times delta 2 times 3 times delta 3. Or this expression I can again write in this form. Delta 1 as delta 2 by 1 by 2 equal to delta 3 by 1 by, sorry, this is 4 here, by 1 by 4. Okay. So you can see that if thermal conductivity is in the ratio of 1 is to 2 is to 4 and your K delta T is constant, so 1, so let us say one first material has 1 watt per meter Kelvin. Okay. So if you look at it here, K delta T is constant. So K, if it is 1, delta T will be 1 value. Then you do K equal to 2. In the second case, because K1 is becoming 2 times K1, your delta T will reduce by half. In the third case, you are having K as 4 times of K1. So your delta T will reduce by 1/4. Okay. So this is the answer. Answer B. So your deltas will be in the ratio of 1 is to half is to 4. Okay. First one, if it is having a delta of 100, second one will be have a delta of 50. Third will have a delta of how much? It will have a delta of 25. Why? Because first one is having a thermal conductivity of, let us say, 1. Second is having 2 watt per meter Kelvin. Third one is having 4 watt per meter Kelvin. Fourth one is having the highest thermal conductivity. It will have a minimum temperature. Okay. So the answer here is B. Let's move to the next problem. Yeah. So probably we have finished all the problems. We have finished all the PYQs. Students, thank you for your time. Thanks a lot.